Huh? Applied to a semiconductor to its operating characteristics or how it operates. Uh, we just got started on bipolar transistors, and we looked at a saturated switch. And the problem we have with these is it's not when we operate them in saturation. So I've got this little circuit hooked up right here, and I'm only using one power supply. And my collector resistor is a 33K. And my, oops, wrong thing. I got it backwards, sorry. My base resistor is a 33K. And we'll call this RB. And my collector resistor, which we'll call RC, is 150 ohms. Now, we use this guy a lot for a saturated switch. So we have three regions we can operate our transistor in. What's the three regions? No, active. So what I'm trying to do, I've got my transistor operated in the active region. So I've got about 5 volts applied to the circuit. I don't know how accurate it is, but and we're doing the same basic circuit that we did with a saturated switch or a switch, transistor switch, but we got it operating. So this is my voltage collector to emitter. So across my circuit, I have, I'll just put it up to 6 volts. I have 6 volts. So if the transistor was saturated, what would I expect to measure across the transistor? Voltage collector to emitter. That is the voltage that we use to determine if the what region the transistor is operating in. So that's a very, very important measurement, is VCE. So if it's saturated, what would it measure? Less than a volt. Okay. Right? Is that pointing the right way? I get some confused. Okay. So this would be great. This would be less than 1, right? Okay. Okay. Then voltage collector to emitter, if it's cut off, what would it equal to? Yeah, so it'll be equal to VCC, because that's what we call that, because that's our power supply. If what would be active? Yeah, so VCE would be greater than 1 volt, but less than what? Yeah, less than VCC. So VCC would be the greatest, right? Everybody understand? So I've got 6 volts applied, and when I come over here and look at my voltage collector to emitter, so this is my voltage collector to emitter. Let me put the camera up. So it's measuring 2.7 volts. You turn it a little bit so I can get it. Okay. So this guy's definitely in the active region. Now the problem we have when we start working with transistors, what determines what region we're in, of course, would be the size of the resistor and then the current gain of the transistor. That makes sense? The resistors. So what I did is I calculated this resistor right here to drop 3 volts. And then, of course, to drop 3 volts is a 150 ohm resistor. I calculated my collector current. So what would that be? It's a 150 ohm resistor. Huh? 20 milliamps? Everybody okay? That sound right? Okay. But to calculate my base current, I need to know the beta of the transistor. What's the problem with beta? Huh? Yeah, that's what it is, but what's the problem with it? It's all over the place. So normally when you look at the data sheets, if you looked at the data sheets, it's got minimum and maximum, but usually they'll have what they call a typical. So typical is basically what you use, but that's not really what it's going to be. So typical beta for the 3904 is 100. So I said, okay, I took that and I divided it by 100, right? Okay, so take that and divide it by 100. And that would be the approximate base current. Are we okay? Everybody okay? Anybody lost? Okay. Then what I would do is I would calculate a resistor that would be required to drop 4.3 volts. Everybody understand that? Yes or no? So that means if this guy right here is dropping, if it's silicon, it's dropping about 0.7. Kirchhoff's law says the sums of the voltage drop in a series branch has to be equal to the applied voltage. So that means this resistor right here has got to drop 4.3 volts. So what I'm trying to do, I'm trying to size a resistor that'll drop 4.3 volts in whatever we got when we divided our collector current by 100. So what did IB come up to be? Approximately what? Are y'all with me? So first of all, I calculated IC. So I said I'm going to set this right at the center. So I'm going to come over here and I want this to be, since I'm putting 6 volts up here, I want this, I'm trying to set this in the active region right in the center at 3 volts. So that means that 150 ohm resistor would have to drop what? 3 volts. So I said 3 volts divided by 150, and y'all came up and got what? Yeah, 20 milliamps. Then I took my typical beta, because I don't know what it actually is. We could actually see it in a minute, but this is good enough for us. So I'd come up here and I would say IB would be equals approximately 20 milli divided by its typical beta, which is a beta of 100. Now remember, beta has no units, right? So why do we come up and get IB? What's that? Got 200 micrograms. Good. Then I calculated a resistor I would need to drop 4.3 volts to get that 200 microamps. So we'll come up here, we'll say, RB would be equal to 4.3 divided by 200 microamps. And what do we get for RB? What's that? 21.5K. Of course, there's no such thing as a 21.5K ohm resistor. So we either got to decide to round it up or round it down. So I went in there. We had a 22K. I put it in there. It didn't work. So I went in there and got the next higher because it was lower than the voltage I wanted. So I went in there and got a 33K, and it looks pretty good. So, you know, when you do these calculations, first thing you got to think about is you got to use A beta to calculate the base resistor, right? You understand? Now, saturated switches, we have no problem. So operating this thing in saturation, we have no problem because we use minimum beta. And what happens to the beta when the temperature goes up? Beta goes up. Well, the problem is once you got it saturated, you can't saturate it anymore. So that's why when we calculate, but to operate it using this arrangement, to operate this in the active region, and I come up here and heat this thing up, things are going to happen. Now, if I did a saturated switch and I had it saturated, I could set that dang transistor on fire, and as long as it's still got its junction, it wouldn't change at all. Because when it got hot, beta would go up. Well, we use minimum beta to calculate that resistor, right? You understand? Well, let's watch what happens. I'm going to come over here, and what I have is I have a soldering iron right here. And right now we got about 2.7 volts using a standard resistor. Now you could get it perfect if you used a rheostat, right? You understand that. But what's the problem with rheostat? Well, first, they're hard to find. So normally we use a potentiometer. What's the problem with a potentiometer? Yeah. Let's go to Jamico and look at the price of a 33 k ohm resistor. So we do a lot of work ordering from this company right here. We've been ordering for years, and it's a really good supply place. Got almost everything you need. Oh, I typed it in the wrong thing. Sorry, guys. And of course, what we would have to use a 100K pot, right? I don't know. There might be a 50 out there. Let's look. So there's a 10K. That wouldn't work for us. There's a 100K. So it costs about what? About 55. Okay, now we're going to look for a 33 k ohm resistor. Oh, okay. I'm sorry. I saw the top. So let's go down and get the 30. So there's a 33K. Less than 10 cents. So if I was going to build 1,000 of these things, right? Look how much more it would cost me if I used the pot over the watt, over the resistor. So odds are we're going to use a standard resistor, right? You understand? And then we're going to live with the difference between our calculated and what we got. And we'll save a ton of money. So that makes sense. So what I'm going to do is I'm going to come over here and no matter what I did, if I come up here and do this, okay, so notice what have I got here, right here? I got a soldering iron, and I'm going to come up here and put it up toward the face of the transistor. And what do you notice immediately? Voltage to collector emitter is dropping like crazy. So the beta of the transistor is going up. If the beta of the transistor is going up, then the resistance of the transistor is going down, which means it's going to drop less voltage. And of course, my 150 ohm resistor is dropping more. And believe it or not, this would eventually, if I could leave it on here long enough and it didn't melt the plastic, this sucker would go into saturation. So what we got to do is we got to come up with a method where temperature doesn't affect the circuit. Now, the type of bias this is what we call base bias. Base bias works great for saturated switches. Works great. Because what do? Well, we use minimum beta. And if we heat it up and beta goes up, it can't go into saturation more, right? You understand that? So these guys work great with switches. They're great with switches. But if I was going to use this in a stereo amplifier, if I was going to bring an input into this, right now, we're going to bring our input in over here, by the way. And we'll look at this later on. So our input would literally come in over here. And we'd put a capacitor in there. We'll talk about that later on. That's where we'd bring our input in. Well, the problem is if it got hot, I would get more gain, right? So the volume of my stereo would vary with temperature. That wouldn't be fun, would it? So we're going to look at some more different ways we can bias the transistor to prevent it from going into what we call thermal runaway. So this is thermal runaway. So it's dropping a voltage. If the beta goes up, the resistance goes down, but the current is also going up. Remember, I square R, right? So even though a resistance is dropping down a little bit, the current has a lot of effect on the power because it varies with the square of the current, right? You understand that? So I might, and if it squares, then more current flows through that voltage, even though the voltage is less, which causes now the transistor to start getting hot on itself, right? You understand? So the transistor gets hot because now it's dissipating more power. Beta goes up. Resistance goes down, current goes up, but power varies with the square of the current, not the resistance, the square of the current. So it sees more current through that voltage drop, which causes it to what? To get hotter, which causes it what? Beta to go up. So these transistors, this thing right here, this transistor would literally go into thermal runaway, which means under the right situations, it would just sit there and do what? It would just saturate by itself. So that means if I'm going to use a transistor as in the active region, and that's what amplifiers are. Amplifiers are active regions. Y'all understand that? So it means all those transistors inside your car radio or inside your TV and all that kind of stuff are not using this guy right here. Because why? We're operating them in the active region, and base bias would go into thermal runaway. So we're going to have to go different ways. So if we call this base bias, what would you think the two other ways we could bias a transistor? Emitter bias and collector bias. So next class, that's what we'll start looking at. We're looking at the different ways that we bias it. This guy is used all over the place as a what? Starts with S. A switch. All over the place. We use this guy all over the place as a switch. Works real well, does a real good job for us. We don't use it as an amplifier. Because of why? Eventually it would go into thermal runaway. You understand that? So a collector bias and emitter bias, these are two biases that we use to prevent thermal runaway. Probably the most popular is emitter bias, but we'll look at the best. Collector bias, you sacrifice gain to keep it from going in thermal runaway. Emitter bias, you don't sacrifice that much gain. You sacrifice a little bit, but not near as much. And so emitter bias is probably one of the most popular biases used in transistor or in amplifiers, or operating the transistor in the active region. Are we okay? So what is that inactive region? That's like what? Rheostat. But what's controlling the rheostat? Base current, no voltage. Bipolar transistors use a current to control a current. It's just that the current it is controlling is a lot larger than the current doing the control, right? You understand? So base current controls the rheostat. So the more base current you put in there, the less resistance the transistor has. The less base current you put in there, the more resistance it has. So it varies opposite of what? Of your base current. So a bipolar transistor, current to control a current. Now we get into FETs, it's going to be a voltage to control a current. So your answer would have been right. Everybody okay? So some of y'all are fixing to do your BJT labs. After that, we got a handout lab that we'll do. I'm going to hand y'all out the labs that we're going to do. I can't remember how many there are.